Hello, everybody. Welcome back to seminar. Hope you had a good spring break. Today we have Dr. Laura Sunberg from CSU Boulder. Just freshly started as a professor there after her postdoc there, and previously got her PhD at Stanford. And is going to be presenting today on microplastics and all things environmental fluid mechanics. So very excited, and let's all welcome her.
Thanks for the introduction, and thank you everyone for having me here today. I've had such a great afternoon meeting so many of you. So thanks so much for hosting me here. And yeah, like Sam said, I'm in my very first year as an assistant professor, so just getting started with getting my lab going. And so everything I'll be talking about today is work from my PhD and postdoc. And I'll be talking to you today about microplastics in the coastal ocean, and specifically the interplay between the properties of microplastics and coastal flows. So what are microplastics? As I've been presenting over the years, I've found more and more people, for better or worse, are knowing what they are, because we continue to discover more and more how prevalent they are and how much they affect us. So you might have heard of them in the news. There are a lot of microplastics in the ocean. They're small pieces of plastic. They're officially defined as being less than 5 millimeters in size. So they're actually not necessarily micro. And a lot of plastic enters our ocean every year, as you might have heard. It's upwards of 5 million metric tons annually, which I know is hard to conceptualize what that means. Volume-wise, that's equivalent to about 50,000 semi-trucks or 250 100-car trains of plastic entering the ocean, which is a lot of plastic, and that's every year. However, the ocean's really big, so you might think, well, relative to the size of the ocean, does that really matter? And the thing is, once plastic enters the ocean, it breaks down into smaller and smaller pieces. And once it becomes these microplastics, they go everywhere. And so they've been found in literally every part of the world's oceans, including the bottom of the Mariana Trench and the Arctic regions, everywhere. So why are microplastics a problem? I would argue that, first of all, they're a problem just because there are so many of them. So we're going to play a little guessing game. There was a study all the way back in 2011, so a while ago, where they went to 18 beaches around the world and they sampled coastal sediment or sand. And they counted how many microplastics were in that sand. And they were using advanced techniques so that they could uncover even the smallest, like nanoscale microplastics. So I want you to guess with me. They found between 2 and 30 microplastics in every specific volume of sediment. So I want you to guess with me what that volume was. A, it would be 250 milliliters, like this. B is 20 liters. C would be 300 liters, like bathtub. And D, swimming pool, 100,000 liters. So if you think the answer is A, raise your hand. B, raise your hand. C, D. We got takers for every single choice. Good job. I love the distribution. The correct answer is A, actually. They found between 2 and 30 microplastics in every 250 milliliters of sediment. And as a reminder, they were looking at truly microscopic microplastics, but still, that was around the world, which is crazy. And we are still, since microplastics are a relatively new pollutant, we're still learning what all of their impacts are, which is somewhat risky. But things we do know, so first of all, problem because there are a lot of them and we don't know everything they do. But one thing we do know that they do is they tend to accumulate chemicals. So these could be chemicals from the manufacturing process. There are tons of different additives used to make plastic, or they could be any chemical they interacted with in their lifetime. So any organic chemicals. They'll also tend to collect metals as well, all kinds of things. And the problem with that is due to their small size, microplastics are easily ingested by fish. Fish are often able to dispatch or pass the microplastics through, but the chemicals that were on the microplastics stay in the fish and can, there's a risk that they could be bioaccumulating in the fish. So to give you a sense of how many fish are ingesting microplastics, there's tons of different studies on this with different methods. But for example, one study went to a fish market in San Francisco and a fish market in Australia. And they bought fish at each of these fish markets, and then they just sampled the guts of the fish. And they found microplastics in a quarter of the fish that they bought. And these are just the ones that happened to be in the microplastics when they got caught, or happened to be in the fish when they got caught. There are additionally studies showing that if you raise microplastic concentrations high enough, eventually, as fish keep ingesting them, one does get lodged in them and can eventually disrupt their digestive processes, their ability to reproduce, all kinds of things. We're generally in the environment not quite at that level yet where we're seeing those extreme impacts, but we're increasing the amount of microplastics every year. So we have a lot of different questions about microplastics still. And some of our big ones from more of a coastal oceanography, fluid mechanics standpoint are, where actually are the microplastics and where do they go? Because they're so small, they're extremely laborious to measure and find out where they are. And so we need to have a better physical understanding of where do they go. And maybe more specifically, if you have a source of microplastics, for example, a river, a lot of microplastics enter the ocean through rivers. How much are they going to spread from that source? And another key question is, how long does it take them to settle? Because the time they have in the water column is all this time that they can, fish can be exposed to them and potentially ingest them. And so how long is it that they actually are in the water column? And these questions are hard to answer for a variety of reasons. One is, if I show you this picture of microplastics again, you can see that they have a lot of different properties. So they're defined as being less than 5 millimeters in size, which is small, which means they're easily carried by coastal flows, but it's not minuscule. They can have some inertia of their own, so they're not going to perfectly follow the flow. There are lots of different shapes, and there are also lots of different densities. They can both be both positively and negatively buoyant, and their density can change over time. And all of these properties are going to impact how they're moving through coastal flows. In addition, there's lots of different processes that impact where they go. And so just in coastal waters, I know I started at the ocean. I'm focusing now on coastal waters because that's where there's really rich ecology and where a lot of people live. So therefore a lot of plastic and also more impact on us. So within coastal waters, microplastics can be ejected by currents. They can be mixed around by turbulence. If they're floating at the surface, wind can push them along, and waves can also impact their transport. One thing waves can do is they can push them onto shore, and once they're on shore, they're more exposed to sunlight, and sunlight tends to photooxidize them, which makes them more brittle, and then they're subject to fragment and break into smaller pieces, especially when they're subjected to the pounding of the surf. They can also be ingested. And then there's also this process called biofouling, which is this layer of organic matter can grow on the surface of them, and it tends to be denser than the ocean water and can cause an initially floating microplastic to sink in really just a matter of weeks to months. So for this talk, we're not going to talk about all of these. We're going to focus on the impact of waves and currents, and then also talk about biofouling. And these specific processes and how they impact where microplastics going and how long are they spending in the water column. So outline for today, we're going to talk about an experiment we did to measure the dispersion of microplastics. I'll get into what I mean by that in a moment, in both waves and currents. Then we're going to talk about a small scale simulation we did looking again at dispersion in waves and currents, but for smaller microplastics. And then we're going to zoom out to regional scale microplastic transport and look at how microplastics biofoul at a regional scale with a coastal model. So jumping in to microplastics dispersion in waves, I'll now give you the more specific motivation. So dispersion is directly, it's how much do microplastics spread from a source. So you have a river going into the ocean, how much are the microplastics spreading? That in and of itself is an important thing to know. But dispersion is also important because it's a model parameter. So when we are modeling microplastic transport at a large scale, we really have just two knobs to turn for their transport. And one is their settling velocity, and the other is their dispersivity, or what is their random walk in a scale like, if you've learned that term before. And so we need to know dispersivity so we can model microplastic transport in general. And we're specifically looking at microplastic transport in waves. Waves are really important in coastal areas, and they affect how stuff moves. They tend to drive onshore transport, and they can modify particle orientation, which means microplastics are lots of different shapes. So if waves are impacting how they're oriented, then they have potential to really impact their transport as well, or their dispersion. And waves so far have been somewhat ignored in the coastal modeling just because we haven't known what to do with them yet, or whether they're important. So we did, in terms of modeling microplastic transfer, of course, waves are used in lots of things in coastal modeling. Okay, so to study this, we did an experiment. We did this in a flume, and we had a weak current, so not turbulent, and then we were generating waves at the opposite end, and so we had waves and currents, and then we released microplastics at the top of the flume, and they were negatively buoyant, so they settled over time and eventually landed in these catch grids we had at the bottom. And because they started all at this single point at the particle release, then when they landed, we could measure the spread in their landing positions to understand how much they dispersed while they were in the flow. So that's the general overview. I'm going to walk you through some different components of the experiment now. This is our wave maker. These are what our waves looked like. So we had linear surface gravity waves. And then we put into those waves our experimental microplastics. So I mentioned microplastics have a lot of different sizes and shapes. So we wanted to have microplastics with different sizes and shapes for this experiment. So first we had discs, and we matched them with their long dimension of 7 millimeters, and then we varied their short dimension from 1 to 2 to 3 millimeters. We also had rods, which had the same long dimension as the discs of 7 millimeters, and actually the same short dimensions as well. And then as an intermediate case, we had cylinders with aspect ratio 1. And the large cylinders you see there are 7 millimeters by 7 millimeters. But those are kind of big volume-wise to compare to the other two cases. So then we had two smaller cylinders volume-wise as well. And we released these microplastics into our flow. And they traveled downward, they traveled downstream, and they eventually landed in the catch grid at the bottom. I'll let you watch for a second because it's just kind of fun to watch. Okay, so they land in this catch grid, and once they've landed in the catch grid, we measure the standard deviation of their landing positions to understand how much did they disperse while they were in the flow. So now that you have seen the setup, we can move on to what our actual results are. And first, I'm just plotting here. So y-axis is the standard deviation of their landing positions for the no waves case. So this is just a current. And I'm plotting against particle eccentricity. If you're curious, the definition is up there. You don't have to pick, you can just look at the shapes here. An infinitely thin rod has eccentricity of 1. And an infinitely thin disk has eccentricity of -1. And the aspect ratio 1 cylinders are right at 0. So the blue points show you what the dispersion looks like with no waves. What about with waves? With waves is now plotted in red. And you can see by eye right away that the spread when there are waves is greater than the spread when there are no waves. So waves are increasing the dispersion of the particles. Of course, it's really hard to see exactly how much if you're just looking at all of these points here. And so to really understand how much are waves increasing dispersion, we should take a ratio. So we just take a ratio between the standard deviation with waves and the standard deviation with no waves. So a ratio between the red points and blue points. And that is what I'm plotting on this next plot. So x-axis is still that particle eccentricity, and the y-axis is now that standard deviation ratio. And first, we can see the magnitudes of these values are almost all greater than 1, except for these large cylinders, which are the big circles. And so the waves are indeed increasing dispersion, and sometimes quite a bit. The most extreme case is the thinnest rods, which is that tiny triangle at the end there. And in that case, the waves increased dispersion 4 times as much as it would have been without waves. So that's quite a big effect. And even some of these smaller cases, like right here, that's still 120% increase in dispersion by the waves. So they're definitely having an effect. The other thing we see is that how much waves increase dispersion changes depending on the particle, and is changing with particle shape. So the thinner rods are more dispersed by the waves than the thicker rods, and the thinner disks are more dispersed by the waves than the thicker disks. So shape is having an effect on how much the microplastics are dispersed. But also the aspect ratio on cylinders all have the same shape, and they are dispersed differently by the waves, which leads us to think we should look into the effects of particle size as well. And so we do that using an Archimedes number, which is the ratio between gravitational and viscous forces. This is the formula for it: gravity, volume of the particle, density of the fluid, rho p is particle density, and then some viscosity on the bottom. The volume of the particle is the only thing that's changing from case to case here, and so really we're just plotting against particle volume. This is just a way of normalizing our values. Particle density does change a bit from particle to particle, and that's why we have these horizontal error bars. They're expressing the variation in those particle densities. So what we see is that it is indeed true that the bigger particles are less dispersed by the waves than the smaller particles. And that might fit with what our intuition would be. A bigger particle has a higher Archimedes number. It's going to plummet through the waves more and be less pulled about by the waves. So one question, though, that this plot leads us to ask is, maybe the bigger particles are just spending less time in the flow, and it's not truly that the waves are really dispersing them less, it's just that the waves have less time to disperse them. So dispersion is dependent on K, which is like dispersivity, so how much are the waves truly actually dispersing them, and also dependent on time, which is like how much time do the waves have to disperse them. So we should check maybe the bigger particle, maybe there's just a time effect going on here. And to check that, we use a ratio between the mean distance that the particles travel. So we've been looking at how much they spread in the flow. Now we're looking at how far did they go in the flow. And that's proportional to how much time did they spend in the flow. And so by taking a ratio between the means in with and without waves, we can say that's roughly similar to the time they spent in the flow with and without waves. So we plot the standard deviation ratio against the mean ratio, and we do see that the standard deviation ratio does increase with the mean ratio, which is what we would expect to see if the particles were dispersing more just because they spent more time in the flow. However, if it was only because of that, we would expect all of our data to collapse on this square root of the mean ratio line, the dashed line here, and you can see that it very obviously does not. The slope is much, much higher. And so although it is true that particles that disperse more also do spend more time in the flow, that's not the only cause. Like the waves are truly actually leading to more dispersion of the particles, not just through keeping them suspended in the flow longer. So summarizing these results, waves matter. This is actually a really important conclusion because we often assume that they don't matter, but waves actually do increase how much particles are dispersing, sometimes quite a bit, up to 400% in the case of those thinner rods. How much waves increase dispersion depends on the particle properties. So more thinner rods were more dispersed by the waves than thicker rods, and thinner disks were more dispersed by waves than thicker disks. And particle size also matters, with larger particles being less dispersed by the waves than smaller particles. So let me take a drink of water. Okay, so from this experiment, we saw that particle characteristics, flow characteristics both matter, but it left us with a lot of questions. For example, shape versus size effects. We can't totally parse out what's happening due to shape, what's happening due to size. We can say that they both matter, but we can't really say for sure what's doing what exactly. And also there's a ton of other parameters we didn't get to explore because in an experiment you're somewhat limited in how many experimental runs you can do. And so because of this, we decided to do a simulation so that we could more fully explore the parameter space. However, once you do a true simulation, you really do need to shrink down we had to shrink down our particles. And so as we're moving into the simulation, I do want to note that we're moving into a regime of smaller microplastics. So I'm going to walk you through all the parameters. It's okay if you don't remember all of the parameters. I just want you to see like the different things that are at play in this system. So first of all, with particle eccentricity, which you already saw, particle shape, The particle size, which I'm representing by the ds, a characteristic length scale of the particle. The density of the particle, rho p, gravity. We also have wave number k, wave amplitude a, the current velocity u, and then the flow, viscosity, and density. So this gives us 9 parameters, and there are 3 dimensions, length, mass, and time. So if you have learned Buckingham pi before, you might realize we can now make 6 pi groups. There's 6 groups of non-dimensional numbers, and we can say that dispersion is going to be, non-dimensional dispersion is going to be a function of these 6 pi groups. So I'm going to show you what the pi groups are, and once again, not expecting you to remember them all, just showing them to you so you know what we're looking at. So first of all, we had 2 you've already seen before, so you should remember these ones. So Archimedes number, which is gravity to viscosity ratio, and then eccentricity for particle shape. We also have the wave steepness, Ka, to characterize the waves. We use a Coulomb-Carpenter number, which, because of the way we end up defining all of our other non-dimensional numbers, this one ends up just scaling with the current strength. Due to the way we've set up this problem. That doesn't have to be the case. And then we also have a Stokes number, which is a typical number for talking about particles, which is a particle response time, in our case, compared to the wave period. And then we have this one I do want you to remember. This is the other special one, is a timescale ratio between the settling timescale of the particles and Stokes drift. So it's kind of expressing timescales of settling versus timescale of waves on the particles. And then last thing, we do need to non-dimensionalize our output since everything else is non-dimensionalized. And we actually have only 1 horizontal length scale in the problem, so it makes it easy. So we non-dimensionalize it by the wavelength. So now we can say that this non-dimensional dispersion is a function of these 6 parameters. And now to explore the impact of these parameters on the dispersion, we set up a simulation. So for this simulation, we use this equation that's called the Maxey-Riley equation, and it's a way of describing what happens to small particles in a flow. And then because our particles have different shapes, we also use fancy name Euler's equation for rigid body motion. What we really mean, if you have a torque, you get the particle is going to change its orientation. And then we set up the flow similarly to our experiment, where we have a uniform current. We now have a uniform current. We do still have a current. And then we have deep water linear surface gravity waves. So, okay, this is just if you're interested in the details. If you're interested in the details, we're including advection, added mass, Stokes drag, buoyancy, Jeffrey torques, and inertial torques. Importantly for everyone, whether or not you're interested in the details, we are assuming a Stokes number much less than 1 because that's an assumption that goes into the Maxey-Riley equations. And so we are thinking about much smaller microplastics than we were thinking about before. We are not including particle-particle interactions, which is fine because microplastics, even though there's a lot of them, they're still somewhat sparse in the ocean. Also, again, just if you're interested, we're not including Bassett history or Staffman lift. Okay, and our initial conditions are we start the particles just below the surface, and we start them at different wave phases and with different orientations. If they all started the same wave phase, same orientation, they would all end up in the exact same spot. So the starting at different wave phases with different orientations create the potential for there to be dispersion. And we run the particles down until they reach a depth where the waves are 90% diminished. And that's where we take, once they reach that point, that's where we take the standard deviation of their positions. Okay, so we had 6 pi groups and we explored them all in lots of directions. So I'm not going to show you all that data because it's a lot of data to look at. I'm going to tell you the results and show you a few interesting plots. So first of all, one of our results is that everything actually mattered. It would have been nice if we could say, oh, it's just this one non-dimensional number, but actually they all mattered to dispersion and all affected dispersion. However, the most important one was this timescale ratio between the settling timescale and the wave timescale. And this had the biggest impact on dispersion. When this ratio was higher, that meant the particles were in the waves for longer and they dispersed more. And when this ratio was lower, that meant the particles were in the waves less time, they dispersed less, which fits with everything we would have expected to see. So this was the most important, but I'm going to show you a few other things because everything did matter. Archimedes number, which we looked at before, had a non-monotonic effect. Also see how much smaller this effect is. It's the same scale as the previous plot. So when we had a bigger particle, it was less dispersed by the waves than most of the smaller particles, but if the particles were small enough, the dispersion actually went down again. And we think that's just because when the Archimedes number is really small, your particles are basically tracers, and they need to have a little bit of mass to actually be doing anything different from the flow and actually truly get dispersed. But over here, this is a similar effect to what we saw before, although again, I'll just note the magnitudes of these Archimedes numbers are way smaller than what we saw before because we're staying within the bounds of what's appropriate for the Maxey-Riley equation. Shape. So on this plot, I'm showing you the impacts of shape, which actually change depending on the Archimedes number. And in all of these experimental cases, disks, well, if anything was more dispersed by the waves, it was usually disks. So in a smaller Archimedes number case, then the thinnest disks were more dispersed by the waves. But as the Archimedes number increased, the dispersion, the shape effects kind of washed out and became less important. And again, I once again remind you, these are much smaller Archimedes numbers than we had before, so we're in a really different regime than we saw before. But we're seeing here that there's like a really intimate connection between the impacts of Archimedes number and shape. Impacts of shape tended to change depending on what parameter we were looking at. So in this case, I'm now plotting Coulomb-Carpenter number on the x-axis, and I'm in this one again scaled with just the current speed. And if you had a faster current, okay, and then each of these colors shows a different particle. So the blue with this little disk symbol is showing the disks, and the red is showing the rods, and the black is showing the aspect ratio 1 cylinders. And you can see that the shapes of these curves actually change depending on the case. And so rods specifically have different dispersion, and the aspect ratio 1 cylinders have different dispersivity, or sorry, these are now spheres. They have different dispersivity depending on the Coulomb-Carpenter number, while disks, it's like once they're getting dispersed, they're just getting dispersed, and it doesn't matter what else you change, they're just dispersing a certain amount. Which, when we were looking at the particle orientations, it seemed to make a lot of sense with the particle orientations. Rods have this ability to orient so they're just spinning in the flow, versus disks are really kind of always flopping around and can get really more mixed about because of that. So, summarizing these dispersion simulation results, the settling wave timescale ratio mattered the most to how much particles dispersed in this wave current flow, but everything else mattered too, and it would be inappropriate to say that's the only thing you need to pay attention to because it's a complicated system. So after these two projects, we can see from them microplastic properties are mattering a lot. But in the environment, microplastic properties change over time. And maybe the most dramatic way they change is through biofouling, which is, again, when this layer of organic matter goes on the microplastics and can cause originally floating ones to sink. And so for my postdoc work, we looked at what is the connection between biofouling and regional scale transport. And really focusing in actually on how does biofouling vary in time and in space in a coastal region. Another side motivation of this project was to understand how regional models work, because I ended both of those projects being like, well, models really need to account for waves and models really need to account for particle properties, but I didn't actually know how the models worked, so I didn't really know if that was possible or how they could do it. So that was another motivation for this project. So, prior literature on biofouling, there was a group that previously developed this model for how you can parametrize biofouling in an idealized way, but still get at a lot of the physics and see especially how do the local conditions that a particle experiences, how do they impact the amount of biofouling on it? Because If there's not a lot of light, they're going to biofoul less. And if there's a lot of light, they're going to biofoul more. And there's other factors as well. This model has actually been used at a global scale to try to understand how does biofouling vary globally. But what we really wanted to do was understand, all right, let's go in between these scales at a coastal scale. How do biofouling rates vary in time and in space at a coastal scale? And therefore we can like really zoom into what's happening. So we chose to do this in the northern Gulf of Mexico. We're in the region where the Mississippi River discharges through Atchafalaya Bay and the Mississippi River Delta. And this is a good choice. One reason we chose this is because we have river discharge and a lot of microplastics enter the ocean through rivers. And actually the northern Gulf of Mexico has especially high microplastic rates compared to other studies of other areas. We conveniently also had an existing regional ocean model for this region, which is a coupled hydrodynamic biogeochemical sediment transport model, and it was a ROMS model, which means that it included information about the flow, which we need to understand how are the microplastics moving, but also included information about the biogeochemistry, which we need to understand how is biofouling progressing on the microplastics. So we took these existing model outputs and then we did offline particle tracking through them. So what this looks like is you take your particle at a certain point of time, it's at this location, and then you say, well, advection is going to be this. And then there's some amount of mixing due to turbulence or dispersion, like we were talking about earlier. This is where the dispersion comes in. And there's also potential for vertical behavior, which in our case is going to be due to the biofouling. And then that gives you your like next position, and then you keep running like this. So to parameterize the biofouling, we followed existing literature for this. And we looked at different processes that impact the total amount of phytoplankton or algae on a microplastic. So phytoplankton can get onto a microplastic through collisions is what they call it, is when the phytoplankton first meet the microplastic. Once they're on it, they can grow. Due to light and nutrients, they can also die. That's mortality. Once they're dead, they'll remineralize or decay over time. And then they can also be grazed by zooplankton. So these are plankton that eat other plankton. And putting all these processes together, so we parameterize each of these processes following previous results, and then taking them all together, we say this is the amount of biofouling on a microplastic, and this therefore is their settling velocity. And that settling velocity we get from all of this is what we input as a behavior into our particle tracking model. So what that actually looks like, I'm going to show you an example trajectory of a microplastic being released at Atchafalaya Bay. This is a plan view, this is a depth view, and the green, I should go ahead and say play it. The green is showing you a biofouling microplastic, and then I'm also showing an orange microplastic that's not being allowed to biofoul, so we can compare the transport. So at first, nothing's happening. It's still staying on the surface. There's not enough biofouling happening yet for anything to happen. These bottom lines are showing you the bathymetry. And eventually, it sinks. It reaches negative buoyancy. And actually, depending on what exactly is going on, you can get an oscillation effect because of once the microplastic starts sinking, it's less exposed to biologically favorable conditions, the biofouling dies off, it starts rising again. We really focus our analysis on this point when they first start sinking, because there's a lot in here. At this point, there's a lot of other considerations you probably should take into account that we don't really have a good theory to account for yet. So we really just focus on how long does it first take them to reach negative buoyancy? When are they first going to start sinking? And now I'll show you the data for all the data, actually. So what we do is we release 500 microplastics from Atchafalaya Bay. We release them once a week for a year. And we track them as they move, and then they're also biofouling as they're moving. And so you can see their green colors getting darker as they're progressing. And we're interested in looking for, like, how long does it take them to first reach negative buoyancy? This is starting in the winter, which is a little boring, I'm going to fast forward to summer. They biofoul really fast, and that's why you see so many like disappearing from the simulation. They disappear just when, in this plot, they disappear when they first reach negative buoyancy. So one thing we should talk about very briefly, a huge part of the study, which I'm really not going into, is sensitivity tests, because there's a lot of details about biofouling that we don't really have nailed down. But I do want to just emphasize that the main thing we saw sensitivity to was the collisions rate. So what rate are phytoplankton first getting onto microplastics? And that is very poorly understood so far in the literature. And depending on, so this is varying it within a reasonable range. Depending on what we set it as, we'll get very different results and very different times to negative buoyancy, which will allow the transport to look very different as well. So this is a key area needed for further research. We looked at all of our data, all of the times to negative buoyancy all together, and we selected this collisions rate to match with what observational data shows is like a reasonable range for times to negative buoyancy. But we need a lot more data here, and this really needs to be more parametrized. And so the results you see next, you should think more about like, how do things compare relatively, and not like, oh, that's exactly what happens in the northern Gulf of Mexico. They take exactly 6.2 days to reach negative buoyancy or something. Like, have to take it with a grain of salt. But that said, let's look at results. So our main question, kind of leading question, is how long does it actually take the microplastics to reach negative buoyancy? And again, we calibrated this with collisions rate, but how does that change throughout the year? And so here on the x-axis, I'm plotting the release date, and the y-axis is the days to negative buoyancy. And black dots show the median time to negative buoyancy. And then this background histogram shows, shows the distribution of times to negative buoyancy. Note that there is this row at the top of particles that never reach negative buoyancy. So depending on the time of year, they could get beached more frequently, or they could get exported from the domain in like a particularly strong river flow. And so we don't always see the moment where they reach negative buoyancy. So these medians aren't like true medians of all the particles, they're medians of the particles that reach negative buoyancy. But what we see is that in the summer, they reach negative buoyancy a lot faster than in the winter. That makes sense. Conditions tend to be a lot more biologically favorable in the summer than in the winter. But it actually changes quite a bit from week to week. So there's like a week difference in times to negative buoyancy just from one week to another right here. And so there's also a lot of like short time scale variation in times to negative buoyancy. And then there's some spread too, and the amount of spread in times to negative buoyancy is also kind of changing throughout the year. So we have, I'm realizing I'm close to how long I should spend on talking, so I'm going to go through the next part of this a little bit more quickly. But we have looked at different like causes of how and why do biofouling rates vary. And first of all, the biogeochemical fields themselves vary temporally. So these are, the top plot is phytoplankton concentrations, and then the middle plot is surface growth rate, and then the bottom plot is surface grazing rate. And you can see that all three of these also vary throughout the year and have a seasonal cycle. So it makes sense that these have a seasonal cycle. We should be seeing a seasonal cycle in our biofouling rates. We are also interested in, are there spatial causes of variation in biofouling rates? And so we did an experiment where we put out a bunch of microplastics in our model, and we held them in place and tracked how long it takes them to reach negative buoyancy. So we can see how do biofouling rates vary spatially. And they actually vary spatially quite a bit. In every season, there was kind of this region which close to Atchafalaya Bay, it's a bit before, and it probably has to do with the wake of the Mississippi River, actually, where biofouling rates are really slow. Everywhere else, they're faster, and it's kind of harder to see the rest of the variation because of how dramatic these are. These are like 60 days compared to everything else is in the like week to month scale. But within everywhere else, we also see some variation moving from the coastline and moving along with the river plume, even though I know you kind of have to squint to see that in this scale. So there's also spatial variation in biofouling rates. And that also makes sense because there's spatial variability in the biogeochemical fields. So I'm just showing you for spring right now, but these biogeochemical fields are constantly changing spatially and temporally. One thing I didn't mention in the previous plot is these purple dots. I'll go back because they're a little easier to see here. The purple dots show you the real microplastic transport because they're actually moving through these variable fields, and how they're moving is going to matter to how fast they actually biofoul. And so you can see in the fall, they get way more spread out versus in the other seasons, they tend to follow the coastline with the river plume. So I'll just summarize that. Microplastics tend to biofoul faster in the summer, but how that really can change a lot from at shorter time scales as well. And biofouling rates change very spatially. So transport and I just want to remind you, transport and biofouling are really intimately linked. With their transport's going to impact their biofouling rate, but then their biofouling rate is going to cause them to sink and therefore really impact their transport. So summarizing overall, microplastic properties and environmental flows interact in complicated ways, and waves, shape, and size can all impact how much microplastics disperse. In our simulation, we found that this timescale ratio between the settling timescale and the waves timescale was most important, but everything else mattered as well. And then from our biofouling simulation, we've looked into how these biogeochemical fields are also going to impact microplastic properties, which will in turn impact transport, but also vice versa. So coming back to microplastics, there's a lot we can pull out for really thinking about microplastics, but I'm just going to leave you with two things here. One, waves enhance dispersion as a function of microplastic properties. And two, the biofouling rates reflect transport through these spatially and temporally varying biogeochemical fields. And from these two results, we can really pull out a lot of information about how much would microplastics be spreading, where would they be spreading, where would they be settling, and when, et cetera. So do want to acknowledge I didn't do this work alone. There are different co-authors for different projects who are all wonderful, and I'll leave these up to take questions. So thank you.
Got a good amount of time for questions. Can you tell us a little more about the density?
Yeah, that's a great question. Yeah, so plastic itself has a range of densities, can be from positively to negatively buoyant. About 40% of plastic is negatively buoyant already. The other roughly 60% is positively buoyant. But it's not like most plastic, aside from like styrofoams, it's not dramatically positively buoyant. It's just a little bit positively buoyant. And algae, especially the type of algae that grows on microplastics, tends to be negatively buoyant. So if you have enough of this negatively buoyant algae on a positively buoyant microplastic, it'll cause it to reach negative buoyancy eventually. Yeah, thanks. Yeah. Oh, sorry. No.
Oh, yeah. So thank you for the talk. Really,
yeah.
Really great. So I guess my question is on your for your dispersion experiment. We do understand shape and size matter. I was wondering if you have looked at whether shape and size would also impact the biofouling.
Oh, yeah, that's a really good question. I have not looked at that, but they do. There have been a couple of studies on this so far. If you have so disc-shaped microplastics, we call them fragments. If you have a fragment shape, they'll tend to biofoul a lot on the bottom, but then not on the top if they're floating. And that obviously matters a lot. Size probably matters, and probably matters quite a bit, but I actually have been having a hard time finding good studies on that so far. It should, in theory, impact what kinds, especially as you're going from nanoscale to millimeter, it should impact what kinds of organisms can grow. But there's not or I haven't found, there might be, I haven't found a good review of what actually happens. But when you get to the millimeter scale, you can actually get bryozoa, which are mollusk-like creatures that do actually grow on the microplastics, and you don't get that with the really small ones. Yeah, great question. You had your hand up a while ago. Yeah, another great question. No, I did not. That's an emerging area of research too. That's super interesting. we're not at, I don't feel like we're quite at the point where we can parametrize it well, but we're close. Like people are definitely actively working on it and it might get there. But yeah, that is definitely a thing that can happen. That is important because it gets sticky with as they biofoul and they're more likely to clump. Yeah, great question.
Yeah, I was thinking about the particle density. Like if there is no any external forces, then the Bowen's force is balanced by the gravitational force, and you get the Stokes velocity. But if there is like more particle, suppose there is no any external force, you release more particle, then the velocity will be more, and there will be less time. So in your experiment, like in your wave experiment, if you use like more particle, incorporate the more particle, do you think the particle density, like the amount of the particle, will affect the size and shape? It will be more dominant factor in your experiment. Do you think like that?
Yeah, that's a good question. Yeah. Well, I'll give a context response first of that. So out in the ocean, microplastics are fairly sparse, so you just don't have the situation with tons of them, except there are so plastic tends to be made out of these little plastic pellets that get melted down to make plastic, and they get transported on ships, and they're really lightweight cargo, and so unfortunately they spill from ships like not infrequently, and then you do have that situation where you have suddenly a ton of plastics all together in the ocean, and that becomes relevant. These are typically though like pellet shaped plastics, so like they're all pretty uniform in shape and size. So context-wise right now, it's not something we've thought about that much, but it is still a really interesting science question. And honestly, something that I haven't thought about too much. Will it matter? Absolutely. And I mean, I think once you get to a certain density, like the shape will impact how they interact with each other, but you're like less concerned about how are the waves actually impacting impacting like this specific shape. Like the conclusions will change quite dramatically from what I have here. Yeah. So great question. Thanks. Yeah.
Well, great talk. That's very interesting. So I got two questions. The first one is more like a comment. It's like a follow-up comment as what DK asked.
Nice.
Because it seems like the biofouling model that you use, you assume that the shape of those particles are the same.
We do, yeah.
Like this.
Yeah.
And as what you say, transport has some coupling effect as the biofouling interacting with each other for the two effects. So maybe there's still an open question, like if we assume different shapes for those particles, and then you change the biofouling rate, and then the transport will be kind of interact.
Absolutely, yeah, that's definitely a huge open question. And also just we didn't incorporate, these were all spheres, and we didn't incorporate how our waves impacting dispersion, which there's also a couple more steps to get there. But yeah, those are great open questions.
Incorporate what you did.
Yeah, totally.
Experiment and try to update.
Totally, yeah.
And my second question is like, because we're in Colorado, so we focus more in river, and like we can also find some microplastics.
Yeah.
But we don't have wave in river.
Right.
I was wondering like how to translate your result into the river condition. I know right now you focus on a kilogram carpenter number, but you're not looking at the Reynolds number because like Reynolds number might be more important in the river condition.
Oh, absolutely,
then, if you look at microplastic as the sediment, once you got high Reynolds number, you got some suspension due to the turbulence.
Yes.
That will probably kind of longer the time that traveling for those particles traveling in the water.
Yes.
There might be an effect. I was thinking about this idea. So do you have any comment on it?
I mean, I agree. It's a great idea, and it is like a research direction I've been hoping to move into, but haven't done anything in that yet. There's some work being done on microplastics in rivers, and like maybe the most interesting has been microplastic resuspension from the bottom of a river. There's lots of other interesting things. Another interesting thing that becomes important is like stranding of the microplastics and how often do they like strand on the shores. But I don't know exactly what happens, and it is like an interesting question. I am curious about trying to move in that direction.
How that turbulence will affect with different shapes and size of the particles.
Yes, that's exactly my current question is exactly that. Yeah, I think both for coastal systems and rivers, there's a ton of research that's been done on particles and turbulence, but it hasn't been with like the specific goal of understanding like dispersion of microplastics, and therefore there's like some key open questions there that we like don't know, and makes it hard to predict everything else. But there is actually a recent study that some Ihui T did, she's actually just started as an assistant professor at University of Ottawa, and she actually did the same experiment I did, but she varied the Reynolds number, and she just published the results. So those are really interesting results, and she found similar. Sorry, I don't know where I was trying to get. She found similar shape and size effects that we did, and that they were both important. So that was pretty exciting to see. Interesting, yeah. Mm-hmm. Yeah. Yes. Yes, definitely. Yeah, Sam.
With the vertical dispersion, how would you measure that in your experiment where you be like these?
Yeah, that's a good question because I said that earlier. I think what we really needed to have done if we had wanted to measure vertical dispersion would just be to have cameras, which we have a camera, but it's not like good enough to measure the vertical dispersion. And then we would have to do it based off of some other metric of like probably time and flow, and say once they've traveled, been in the flow this long, we'll check their vertical position, assuming that it gets a little tricky because you can't include any that have settled, and so you kind of have to constrain your distribution in a way. But yeah, with cameras, which if we'd been thinking about that, we would have taken an extra day to get our cameras a little better for that question, but we weren't.
And also, you're using visually observable microplastics. Mm-hmm. Like, what was the smallest size you used?
Yeah, these were all millimeters, or these were the microplastics. They all had a dimension of, the smallest ones were these cylinders that are 3 by 3 millimeters.
Is there like a way to extend that to even smaller sizes? Like any methods that you know?
Yeah, I think the hardest part just becomes like printing. So we 3D printed these particles. So it's hard to 3D print something too small, but you can buy like specific shapes, are like sold for different purposes. So you can do that. And then other people just like make natural microplastics by like breaking something or whatever, and then you can get whatever like sizes from that too. But yeah. But experimentally, once you're, if you can visualize them, it's much easier. So yeah.
Is there a way to, like, I've heard of maybe using optical backscatter as like getting a measurement in situ of microplastics rather than just like visual? Is there, what methods are you aware of? Like, I'm curious if there would be like any sort of like field deployment you could go out in the Gulf and just kind of get an idea of what's going on with the district.
Yeah, that's a really good question also. Yeah, there has been a little bit of recent research on the optical backscatter, and some people are saying maybe you can even like use satellite imagery because maybe they affect like viscosity and also like color even. I think that was all, I feel a little wishy-washy on that. But there are a few newer like measurement devices that they still have to be like a small area, but they are like much more efficient. So there's like some flow through devices where you just start carrying it under the boat, and so if it's flowing through, and it's still optical, but it is like just repeatedly measuring the microplastics, and that's probably the one that I'm most hopeful about. But I've seen there's a few coming that may or may not end up working well. I'm not sure. Yeah.
But the cameras may easily determine its own plastic rather than like.
Yeah, well, okay, I'm like really stretching outside of what I really know. That's a good question. Sometimes, also sometimes they use like different types of light, and like based on the properties of how that light interacts with plastic. But like I don't know that. Yeah.
So what is the biggest challenge is, like, if you want to scale your findings from laboratory experiment to the natural?
Yeah, that's a really good question. So for like this experiment, I think, and combined with the simulation, we're not far from being able to scale them to the real world. The thing that we don't have is turbulence. And that I think is the most important baseline thing we need to understand is how does turbulence impact the dispersion of the microplastics? And then also if you have waves and turbulence, what happens? Because it won't necessarily just be additive. Yeah, so that's kind of like the next step to like scale these. And then of course there's tons of other effects, but once you have both of those, you really have like your key building blocks, and then you can start thinking about, well, currents, different directions and stuff like that. But yeah, good question. Mm-hmm.